So in gear trains, we will move to the next topic, that is the calculation of torque on the gear train. So in a gear train, there are various gears. It is formed by combination of gears. So you can have different kind of torques applied on different gears, and when you analyze as a system, you can get the relation between those. So I'll draw a diagram here. So the central portion is the gear train system, and we are having an input to the gear train system. So this is input. So there will be some input angular velocity of the input element, and there will be some input torque. Let's say TA. Similarly, this is the output from the gear train, and we will have some angular velocity of the output. Let's say omega b, and some resisting torque at the input. So as you can see here, I've taken the convention the torque to be opposite, because this is the driver. Let's say since the angular motion is in clockwise sense, the torque will also be in clockwise sense. So torque or force is supplied here. It is the input, and the output. Since your shaft is rotating in angular clockwise fashion, your load will be resisting the motion of the output. So output torque is resisting. So hence it is in negative sign. Now apart from these two, the gear system will also be subjected to a clamping torque. The clamping torque can be of any direction. It can be clockwise sense also. It can be in the anti-clockwise sense also. So TC is the clamping torque to hold the gear in place. This is important to consider the clamping torque, because since in the gear we are using a gear train to get a velocity ratio, the main purpose of the gear train is to reduce or increase angular velocity. So since and the power is constant, and T A omega A is equal to T B omega B, power that is constant for no loss. So that's why since the omega is changing, so torque is also changing. Torque will change from input to output. So hence the input torque will not be same as the input output torque, and hence there will be a force imbalance. To counter that force imbalance, you have to apply a clamping. So that you provide by various means such as bearing in the gear train system. So we'll lay down a condition for balance of torques. So if there is no acceleration in the system, no acceleration of the system, since your input shaft and the output shaft all are rotating at constant angular velocity, and the velocity ratio is defined, there is no acceleration as such. So if there is no acceleration, there can be no net torque on the system. So sum of all torque should be equal to 0. Hence TA plus TB plus TC should be equal to 0. So here you should take a convention. So important to remember the direction, to consider direction. If you are considering clockwise as positive, then the torque applied in clockwise should be taken as positive in this equation. And if the torque is anti-clockwise, let's say TB is anti-clockwise, so it should be taken as negative in this equation direction, and hence put the sign to get the correct results according to the directions considered. If in the final answer you get opposite of what you assumed earlier, let's say you assumed that TB is negative and eventually it came out negative, so negative of negative will be positive. So hence it is important to remember your original sign convention and the final result that you got. And apart from the no note Apart from the no net torque condition, you have the power, the energy conservation condition, that is input power is equal to output power, Ta omega is equal to Tp omega B. So by using these two equations, equation 2 and equation 1, you can calculate the torque on the system, since omega A by omega B is known. If you are considering efficiency also, then output power will be efficiency times the input power. Input power is Ta omega A. So these two equations are same, two only. The application of these equations to find out a torque will be clear when we take up a numerical example. Before doing that, we will cover all of our definitions. So the next definition is of compound gear trains. A compound gear train is simply a chain of simple gear train. The simple gear train, you saw that the shafts are coaxial. They are in all the gears are in mesh with each other. So in compound gear chain, we have a chain of simple gear train where the input of second feeds the output of first. So in simple word, the output of the first is connected to the input of the second. I'll draw a gear chain here. So let's say you have a gear drive like this. These are the axes. So let's say this is the input of the first gear train, and this output of the first gear train is again connected to input of the second gear train. So here you again have one more gear, and then it is meshing with, it is driving the second gear chain. The second gear chain may drive some other also. You can have any information, but the compound gear chain term is used when output of first is driving input of second. So the treatment for finding the gear ratio for such train is slightly different. In earlier case, we saw that in simple train, the gear ratio is simply equal to angular speed of input by output, or teeth of output, let's say C by teeth of input, and the intermediate gears didn't used to matter. The number of teeth on the intermediate gears doesn't used to matter. We had like this A, B, C. It can be a long chain, but only output and input number of teeth matter. Intermediate gear, the number of teeth doesn't matter. In this case, we'll do the derivation for gear ratio. Let's say this gear is A, this is B, this is C, and this is D. So we have, our target is to find gear ratio, that is the speed of driver divided by speed of driven. So in this case, it will be omega A by omega D. Now you know that omega A by omega B will be equal to TB by TA, number of teeth, and similarly omega C by omega D will be equal to TD by TC. Now in these two equations, you know that the B and C are same shaft, gears are on same shaft, so hence omega C is equal to omega B. The angular speed of rotation on the same shaft will be same. So multiplying these two terms, we get omega A by omega B multiplied by omega C is now omega B only, and omega D is equal to TB by TA into TD by TC. Omega B gets cancelled out. So this quantity is equal to omega A by omega D, that is speed of driver divided by speed of driven, is equal to gear ratio. So hence in this case, in compound gear train, you have seen that the number of teeth of intermediate gears also matters. These compound gear trains are used in application where you need large reduction ratio, where just one gear is not sufficient. That is another category of compound gear train, that is called reverted gear trains. In this case, the input and the output lie on same axis. They are not connected to each other, otherwise you will not get any speed reduction. They just lie on the same axis. So I'll draw a sketch for that. Let's say this is the input shaft. Okay. This is the input gear. Then you have one another gear where it is meshing. Then you have the shaft of that. In compound train, the output of first feeds the input of second. So now I'm drawing the input of the second. And then you have the final output gear. So this is the output gear. And the axis of that output gear, as I draw here, this lie in line with the axis of the input gear. So if you draw the axis here, both will be in the same line. A is input, B is the output of the first gear train, second gear train, C is the input of the second gear train, and D is the final output. So A and D have same axis. Here also the velocity ratio, the gear ratio is determined by the earlier condition. We go on determining the final output gear angular speed, that is omega t, and we have the driver speed, that is omega d, and this is equal to tb into td divided by ta into tc. So along with this gear ratio condition, you have an additional condition to satisfy here also, that the radius of gear 1 plus radius of gear 2 is equal to radius of gear 3 C plus radius of gear 4. So as you know that gears can be classified in the terms of this cycle radius. They are equivalent rollers that can be replaced by the gear. So if R is the cycle radius, then R of A plus R of B is equal to R of C plus R of D. This is an additional condition to satisfy. Now you know that the module for all the gears should be same. For any gear chain, this is the first requirement, that the pitch of the teeth should be same. Module is defined as diameter by number of teeth. So diameter is equal to module into teeth, and radius will be equal to module divided by 2 into teeth. So if you replace here in this condition, this will be module by 2 will take outside, teeth on A plus teeth on B is equal to m by 2 teeth on C plus teeth on D. So hence TA plus TB will be equal to TC plus TD. This is an additional condition for the reverted gear trains, where the input and output gear lie on the same axis. Now we will come to an important topic in the gear train subject, that is epicyclic gear train. This has a special theory and some intuition is required to understand this gear train, and that's why it's likely that questions may come from this topic. So in this case, we have a gear and the axis of that is connected to an arm. This is the arm, and the other end of arm is also holding another gear. Let's say this one. Let's just trace somewhere here. This is the axis of the first and the second. So in this case, the bigger the gear shown here will be fixed and the arm will be given some rotation. So since this is rotating and these two are in mesh, this is smaller gear. So the smaller gear will start to rotate as well as it will move in the translational direction due to the movement of the arm. So the terminology used here is that the bigger wheel is called a sun since this is a fixed gear usually. Although the modification of that is also possible, that we will cover in the subsequent topics. So for time being, we consider it is a fixed gear, it is sun, and this gear, the smaller gear, will rotate about its own axis. It will have a rotational motion, as well as it will revolve around the sun gear. So this motion is something similar to planet in the solar system where the planets are having a rotation about their own axis and they are revolving around the sun. So this gear is called a planet gear. And then there is an arm which is connecting the sun and the planet. The length of the arm is such that both the teeth of the planet and sun are in mesh. So they will mesh closely. The length is such chosen. If you see the side view of this gear train, it will look something like this. This will be the planet gear, and then you have the sun gear here. This is the axis of the sun gear, this is the planet gear, and the planet gear axis will be joined by a arm with the axis of the sun gear. This is arm, and this is axis of the sun gear. Arm, sun, and planet. So our task now is to determine the transmission ratio in different configuration. The sun can be rotating, the arm can be fixed, and maybe the planet is fixed, the sun is rotating. Different configuration are possible in this gear train. So we will term this planet as B, we term the sun as A gear. So in the case arm is fixed, then the problem is very simple. They are just two gears in mesh with each other. So in that case, omega A by omega B will be equal to number of teeth on B divided by number of teeth on A. So this is very simple. The other case occurs when sun or planet is fixed. So it is whether the sun is fixed or planet is fixed, the motion is pretty much same. Just the gear ratio will change. Number of the larger or bigger will change. That doesn't matter. So for now we consider sun as fixed. So in the case sun is fixed, the arm will have a rotatory movement. You can see here, rotation here, and the planet will have a rotation as well as revolution. In that case, we have to find the angular speed ratio of the arm to the planet gear. So speed ratio will be angular speed of arm, that is driver, divided by angular speed of planet gear. This is not so straightforward because arm is not a gear and you cannot determine from the number of tools. So in this case, we adopt a special methodology. We will list the gears A, B, C in table, and then we'll follow three steps. The first step is revolve all gears clockwise, that is positive 1 by 1 revolution plus 1 revolution clockwise. Okay, so in this case, there is no relative movement between any gear, sun, planet. All of them are rotated about the sun center and everything is locked. There is no relative motion. So revolve all gears plus 1 clockwise and locked. No relative motion between gears or arms or legs. It's just like a rigid body, whole thing is rotated plus 1 clockwise revolution. B also plus 1 and C also plus 1. Then the second step is that revolve C, revolve A, the sun gear. So revolve the sun gear by -1. Since we are considering the case sun is fixed, so first we revolve everything by +1. Now we will revolve only A, that is the sun gear, by -1. So then when we add up, the moment of A is 0. So revolve A by -1. In this case, we are allowing the relative motion between various gears. So this is a critical step in getting the speed ratio. In this case, we are keeping arm fixed. So as you saw earlier, like when the arm is fixed, it's pretty much straightforward to find the angular velocity ratio. So now we have rotated entire. First, we have rotated entire thing about the center, sun center, +1. That means +1. Then and only sun gear -1. A is rotated -1. So in this case, when A is rotated -1, what is the, and arm is fixed. Arm fixed. In that case, we can determine the rotation, number of rotation on of planet gear of the B. So number of rotation of planet gear will be equal to, that is omega B is equal to omega A into TA by TB, and since omega A there is one revolution, so 1 TA by TB. So the B will rotate by plus T A by TB. It is important to consider the sense of the rotation here. So since the sun gear is moving anti-clockwise, so the planet gear will move clockwise. So we have revolved the sun gear A by -1, keeping C fixed. So in this case, the revolution of A will be -1. -1 means anti-clockwise. Revolution of C will be 0. And as we saw here, since the arm is fixed, the angular velocity ratio can be determined as such. And for one revolution of A, B rotates minus TA by TB. So for -1 revolution of A, B will rotate plus TA by TB. So we'll put that value here, plus number of teeth on A by number of teeth on B. And now we come to the third step. In third step, we will add the above moments, above rotations. So add step 1 and 2. So on adding the moment revolution of A, we will get 0. On adding the revolution of B, we will get 1 plus TA by TB, and revolution of C will get 1. So by superimposition of the motion, we have got a condition where A is fixed. That means A doesn't have any motion. Motion of A is 0. And for one revolution of C, B will make one TA plus T by TB revolution. So omega C by omega B will be equal to 1 divided by 1 plus TA by TB. So this is the derivation of gear ratio or velocity ratio of epicyclic chain. So likewise, you can also derive for the case when the B is fixed, the planet is fixed, and sun is made to rotate. In this case, the A and B will just change their positions because the gear size doesn't matter. In this case, the sun will start rotating towards around the planet, and in this table, you just have to follow the same procedure and replace A by B and B by A. Shuffle that. So we will just keep our derivation simple here, and we have found the velocity of B when the arm is rotating and the sun is fixed. We will move on to another derivative of the epicyclic gear, that is epicyclic train with annulus. So here an additional member also comes in picture, that is we have the sun, we have the planet, and we have the leg as drawn here, and this entire assembly is kept around in an annulus. So this annulus is also a gear which is having internal teeth. You can see it here. So the if you zoom in the meshing of the planet gear, the planet gear will have some teeth and the annulus will have some teeth. So they will mesh with each other. And when this is moving in clockwise fashion, it will also move in linear movement. So it is something similar, not exactly same, but something similar to rack and pinion. But here the annulus is having curvature. The pinion doesn't have any curvature. So this is annulus. Let's say the annulus is termed as A, the sun gear is termed as S, the planet gear is termed as P, and the leg is termed as L. In some cases, you will see a three-legged epicyclic train, but basically it's the same structure. In that case, you have like this 123 web. This leg is called web now, and you have three planet gears. P. This is also P. But if you do analysis for single legged or triple legged, the velocity ratio come to be same. Is same. So we can do any kind of analysis you want because the relative moment will be freezed, and this kind of arrangement is made in real system for load distribution. You have three legs. So now we'll go on with the derivation using our standard procedure that we used earlier. So we'll make a table for all the years. We have the leg L, then A annulus, P is the planet, and S is the sun. The first step towards the derivation is that turn entire gear train freezed. So there is no relative motion between different gears clockwise plus one revolution. And that thing will revolve clockwise plus one plus one plus one. All the gears and that thing is frozen. There is no relative movement. Relative movement. Second step, as you saw earlier, uh, that we want to keep one of the elements fixed. In case the leg is fixed, the problem becomes very simple. You just rotate the S and you get by number of TA by TP by TS, you will get the velocity ratio between P and S. And then, so here, if leg is fixed, then omega P by omega S will be equal to TS by TA, and omega A by omega P will be equal to TP by TA. Sorry, here it is TP, TS by TP. So you can get all the velocity ratios if the leg is fixed. But usually you will want the sun to be fixed or the annulus to be fixed. So we have seen the derivation for sun to be fixed. In the case sun is fixed, we will get omega L by omega P is equal to 1 plus TA by TB in that case. So you figure out the name convention, omega C by omega B, which was there. So in case sun is fixed, so sun is fixed also, since you know the angular velocity of P, you can determine the angular velocity of A by this formula. So that is also a solved problem. For that you can refer the discussion we just had in the last page. Now we are solving for the problem or the third part when the annulus is fixed. So this is something new that we will want to solve. Annulus fixed, so we will give -1 rotation to the annulus. So that its resultant motion is 0. Give annulus A -1 revolution. So that means anti-clockwise. And then see the motion of the other part. So A is -1. And while doing that, we will keep the leg fixed. So that's why this whole exercise of table creation is that we don't know the L is not a gear element, it's a leg, and we can't get the uh, like a gear ratio derivation for L. So that's why we in first step give +1 revolution to leg, and then we give 0. We keep it fixed. So in the second step, we are since the leg is fixed, we are able to determine all the velocity ratios. See here, since the leg is fixed, it is very easy to determine the velocity ratio like a simple gear train.